NASA now appears to have a workable fix for one of the latest technical issues affecting the space launch system: the rocket assigned to carry Artemis 2 around the moon. On the surface, that may sound like a routine engineering update, but it arrives at a moment when much bigger questions are gathering around the entire U.S. human spaceflight program. The SLS rocket is still being prepared. Artemis planning is still being adjusted. And even the timeline for the International Space Station is now being pushed into a more uncertain transition period. Taken together, this is not just a story about one seal, one valve path, or one test anomaly. It is a story about whether NASA can stabilize several major systems at the same time. So let's take a closer look. If you value space coverage that explains the system clearly, step by step, this channel is built for that. The immediate issue began during a standard pre-launch procedure known as a wet dress rehearsal, conducted for NASA's Space Launch System rocket. This rehearsal took place on February 21st and is part of the final preparation process before an actual launch attempt. A wet dress rehearsal is essentially a full simulation of launch day operations. Engineers load the rocket with the same cryogenic propellants that would be used during the real mission. They run through the complete countdown sequence, monitor the behavior of every system, and verify that propellants, pressurization systems, and control systems all operate correctly. The only step missing is the ignition of the engines. During this test, engineers detected an unexpected problem. Helium was not flowing properly into the rocket's upper stage. That detail immediately raised concern because helium plays a critical role in how large launch vehicles manage their propellant tanks. The anomaly led NASA technicians to open the launch vehicle stage adapter area inside the rocket structure. This allowed engineers to access and inspect a component involved in transferring helium from ground systems into the vehicle before launch. After a closer inspection, engineers identified the source of the problem. The issue originated inside a quick disconnect connection, a ground interface component that feeds gases and fluids into the rocket while it sits on the launch pad. Once the cause was identified, the engineering team began a repair process and additional testing to verify that the system was functioning again as intended. To understand why this issue mattered, it helps to look more closely at how the propellant system of a large rocket actually works. Inside a launch vehicle, like the Space Launch System, propellants are stored in extremely large tanks. For Artemis missions, the upper stage carries cryogenic propellants, meaning fuels that are stored at extremely low temperatures. These propellants must move smoothly through feed lines into the rocket engines during flights. However, gravity alone is not enough to move propellants reliably inside these tanks, especially as the rocket accelerates and experiences changing forces during ascent. To maintain a stable flow, rockets rely on tank pressurization systems. This is where helium comes in. Helium is an inert gas, meaning it does not react chemically with the propellants. Engineers use it to pressurize the propellant tanks. When helium is introduced into the tank, it maintains internal pressure and helps push the propellants toward the engine feed lines. In practical terms, helium acts like a controlled pressure source. It prevents the tank from collapsing as propellants drain and ensures the fuel continues to move steadily toward the engines. If that pressure system is disrupted, several problems can occur. Propellant flow can become unstable. Engines may not receive the correct mixture of fuel and oxidizer. In extreme cases, the propulsion system cannot operate safely at all. That is why engineers pay very close attention to the helium supply path during testing. In this case, the helium did not fail because of a pump or a control system. Instead, the issue originated at a physical connection between the rocket and the ground systems. This connection is called a quick disconnect. A quick disconnect is a specialized interface used during the pre-launch phase. While the rocket sits on the launch pad, it must receive several resources from ground equipment. These include propellants, electrical power, and gases such as helium or nitrogen. The quick disconnect provides a sealed pathway for those fluids and gases to enter the vehicle. At liftoff, the connection must separate cleanly and instantly as the rocket rises away from the pad. To accomplish this, the quick disconnect contains seals and valves designed to maintain pressure while allowing rapid separation during launch. During the February test, engineers discovered that a small internal seal inside the quick disconnect had shifted slightly out of its intended position. Even though the movement was minor, it partially obstructed the helium line. This reduced the flow of helium into the system and triggered the anomaly observed during the rehearsal. To correct the issue, technicians removed the quick disconnect assembly from the system and disassembled it for inspection. The displaced seal was repositioned, and the internal components were carefully reinstalled. Once the repair was completed, engineers conducted a verification test. Instead of immediately running the system at full operating conditions, they introduced helium at a reduced flow rate. This allowed the team to confirm that the line was clear and that the gas could move through the system without obstruction. At the same time, NASA engineers began investigating why the seal moved in the first place. Understanding the root cause is essential, because even a small shift in hardware can repeat if the underlying mechanism is not fully understood. While this work was underway, technicians continued other preparations for the Artemis mission. One of those tasks involved activating batteries for the flight termination system. This system is part of the range safety architecture used during launches. If a rocket were ever to veer dangerously off course, the flight termination system allows ground controllers to destroy the vehicle to prevent it from threatening populated areas. Other battery replacements were also performed across several key components of the rocket, including the core stage, the upper stage, and the solid rocket boosters. Meanwhile, work continued on the Orion spacecraft, which sits on top of the rocket. Engineers charged the batteries for Orion's launch abort system, the emergency escape system designed to protect astronauts during ascent. Unlike some spacecraft that use a pusher-style escape system mounted beneath the capsule, Orion uses a tower-mounted abort motor positioned above the crew module. If a serious failure occurs during launch, that motor ignites and rapidly pulls the capsule away from the rocket. If the launch proceeds normally, the abort tower is later jettisoned once it is no longer needed. In parallel with these activities, technicians also began replacing a seal within the liquid oxygen feed system on the rocket's core stage. After installing the new component, engineers will reinstall the oxygen tail service mast umbilical plate, which is another ground interface connecting the rocket to support equipment. Once reinstalled, the system will undergo additional integrity checks to confirm that the seal holds pressure and that no leaks are present. All of these tasks are part of the final preparation process before the rocket returns to the launch pad. At first glance, the repair of a small seal inside a ground interface might seem like a routine engineering correction. In many ways, it is. Large launch vehicles go through extensive testing precisely to uncover issues like this before flight. But in the case of the Space Launch System and the Artemis program, the timing of this repair carries broader implications. The Artemis program is designed to return astronauts to the moon and eventually establish a sustained human presence there. The Space Launch System rocket and the Orion spacecraft form the backbone of that architecture. Artemis II, the mission currently being prepared, would be the first crewed flight of the system, sending astronauts on a lunar flyby. Because this mission represents a major milestone, even relatively small technical anomalies receive significant attention. The helium flow issue occurred during a rehearsal specifically meant to reveal these kinds of problems before launch. If the repair and verification testing hold under full operational conditions, it would confirm that the system can proceed toward its next launch attempt. However, The technical work on the rocket is only one part of a larger shift happening around NASA's exploration plans. At the policy level, lawmakers in Washington recently advanced a NASA authorization bill that could influence the direction of the Artemis program. Among other provisions, the legislation reflects NASA's decision not to pursue the previously planned Block 1B upgrade of the Space Launch System. That upgrade would have introduced a new exploration upper stage, designed to significantly increase the rocket's payload capacity. Instead, the agency now appears to be leaning toward maintaining a configuration closer to the current Block 1 version of the rocket. If confirmed, that approach would prioritize operational stability and repeatable launches rather than pursuing major hardware upgrades in the near term. The reasoning behind that shift relates partly to schedule pressure and cost considerations. The exploration upper stage program has faced delays and rising development expenses. Continuing with the existing configuration could allow NASA to focus on flying the system more regularly, rather than waiting for a larger redesign. At the same time, the same legislation also points toward a longer-term objective: the development of a sustained U.S. presence on the Moon. The bill includes language encouraging NASA to move toward infrastructure that could support long-duration missions, robotic operations, scientific research, and potentially industrial activity on the lunar surface. In other words, the repair of a single component on the SLS rocket sits within a much larger framework of decisions about how the United States intends to pursue lunar exploration over the next decade. Another factor influencing these discussions is the growing international dimension of lunar exploration. In Washington, there is increasing recognition that other nations, particularly China, are also developing long-term plans for human activity on the Moon. If Artemis missions experience repeated delays, policymakers worry that the United States could lose momentum in that effort. If NASA succeeds in stabilizing the SLS launch system and maintaining a predictable launch cadence, it could help reinforce the broader Artemis strategy. But if technical issues continue to appear or schedules slip further, pressure to reconsider the architecture could increase. Even though NASA engineers believe the immediate helium flow issue has been corrected, several uncertainties still remain. The quick disconnect repair resolved the physical obstruction that reduced helium flow during the wet dress rehearsal. But engineers are still investigating the underlying reason why the internal seal shifted out of position in the first place. That question matters because launch systems operate under extremely demanding conditions. Components experience vibration, temperature changes, pressure cycles, and repeated connection and disconnection events. If the movement of that seal was caused by a design sensitivity or by operational conditions, engineers will want to understand it clearly before the rocket proceeds to launch. Another milestone to watch is the series of integrity checks and system verifications that follow hardware repairs. Once components such as the liquid oxygen feed system seal and the service mast umbilical interfaces are reinstalled, engineers must confirm that all fluid lines remain leak-free and that pressurization systems behave exactly as expected. Only after these checks are completed can NASA prepare to roll the Space Launch System back to the launch pad. Current planning has pointed toward launch opportunities in early April, with 2-hour launch windows available on several days during that period. Whether those windows can actually be used will depend on a combination of factors, including the completion of technical work, weather conditions, and range availability. Beyond the launch timeline, several broader program questions also remain open. The final direction of the Artemis architecture, including how NASA plans to manage the Space Launch System configuration in the coming years, is still being discussed at the policy level. At the same time, the transition from the International Space Station toward future commercial stations is still unfolding, and that transition will likely shape how human spaceflight operates in low Earth orbit after the early 2030s. In other words, the repair of a small seal inside a quick disconnect solved a specific technical problem. But the larger story around Artemis, SLS, and the future of human spaceflight is still developing. And as these programs move toward their next tests, launches, and policy decisions, the picture will continue to evolve.